Welcome everyone to The Explainer. Today we are taking the incredibly frustrating, hair-pulling trial and error out of deep learning and transforming it into a rigorous scientific methodology. We're going to be unpacking Google's Deep Learning Tuning Playbook. It's this brilliant guide put together by researchers who have literally been in the trenches since the dawn of modern AI, and their whole goal is to completely overhaul how we approach model performance.
Look, if you spend any time working in machine learning, you absolutely know the collective agony of model optimization. Honestly, it so often feels like you're just throwing spaghetti at a wall, right? You tweak a learning rate here, you mess with the batch size there, maybe blindly swap out an architecture, and you just kind of sit back and pray the validation loss goes down. It's this exhausting, never-ending cycle of guesswork, toil, and frankly, relying way too much on pure luck. And let's not even talk about the literal heat and money you're burning in wasted GPU compute while you do it.
So it begs the big question we're tackling today. Is there an actual way to turn this sort of black magic of model optimization into an exact science? Can we finally ditch this exhausting alchemy for a clear, predictable laboratory method that guarantees we're actually learning something valuable from every single experiment?
To figure that out, we've got a 6-step roadmap for today. We'll kick things off by shifting our mindset from alchemy to science, then hit the incremental tuning strategy. Properly classify our hyperparameters, design our search space, learn to read experimental results the right way, and finally, refine and launch.
All right, Section 1, from alchemy to science, replacing luck with methodology.
So before we even think about touching a line of code, we have to fundamentally rewire how we approach this. Let's look at the old way versus the playbook way. The old, chaotic way is trying to maximize performance by changing like 5 variables all at once and just automating a massive search of the entire configuration space right out of the gate. The playbook way, it demands that we make small, incremental changes. We have to isolate our variables and prioritize gathering rock-solid evidence over some short-term bump in performance, because the actual goal here is deep insight into the problem, not just a lucky drop in validation error.
Moving on to Section 2. The Incremental Tuning Strategy, a framework for discovery. To see how this mindset shifts into a real day-to-day workflow, we iterate through these 4 very deliberate steps. Instead of a massive blind search, you do this. First, pick a tightly scoped goal. Maybe you just want to understand the impact of one specific activation function. Second, design a batch of experiments targeting only that specific goal. Third, deeply evaluate what happened. And finally, determine if the evidence is actually strong enough to adopt that change as your new baseline. It's a slow, methodical build of genuine insight.
Section 3. Classifying your hyperparameters. Organizing the lab variables.
Now, to pull those experiments off, we need to borrow a page from high school science class and meticulously organize our variables into 3 distinct buckets. Bucket number 1 is your scientific hyperparameters. Think of this as the star of your experiment. This is the one specific setting whose effect on the model you are actively trying to measure today. For example, maybe you're comparing 2 different optimizers to see which one is fundamentally better for your specific dataset.
The second bucket holds your nuisance hyperparameters. These are things like your learning rate or momentum. They're called nuisances because, well, to get a fair comparison of your scientific variables, say pitting a 5-layer model against the 6-layer model, you actually have to tune the learning rate separately for each of those models. If you don't optimize away those nuisances, your comparison is completely unfair and your results are totally invalid. The third bucket is fixed hyperparameters. These are the variables you intentionally lock in place just to conserve your compute budget. Look, we don't have infinite resources. Now, fixing variables does mean you have to accept some caveats, like your grand conclusion might actually only hold true for that specific fixed setting. But it's a completely necessary compromise to keep your AWS bill from exploding.
What's wild is that a single setting can completely jump between these buckets depending on what you're doing. Take activation functions, for example. If your whole goal is to figure out if ReLU beats tan, then it's your scientific variable. But if you're trying to compare model depths, you might need to tune the activation function for each depth just to be fair, which makes it a nuisance. Or you might just lock it to ReLU while you test out batch normalization, making it fixed. Its label strictly depends on the specific question you're asking that day.
All right, Section 4. Designing the search space, building the experiment.
Now it's time to actually set up the boundaries of our study. When you're building these experiments, a massive question always pops up. Literally, how long should you train your model during these tests? And the answer entirely depends on where your specific bottlenecks are. The researchers divide this into 2 camps, compute-bound and not compute-bound. If you're compute-bound,
meaning time and GPUs are your strict, hard limits, you basically just train as long as you can afford to, maybe doing some shorter runs early on to weed out the really bad ideas. But if you aren't compute-bound, the whole strategy shifts. You want to train just long enough for the model to hit its best result without wasting a single unnecessary step. You usually figure this out by seeing exactly how long it takes to perfectly fit the training set with a constant learning rate.
Regardless of your constraints, you have to strike this really delicate balance to maximize the scientific insight you pull out of the experiment. You've got to compare enough scientific values, make sure your nuisance search space is actually wide enough so you aren't missing the optimal setup, and then sample that space densely enough so you're not just leaving the outcome up to pure luck.
Section 5. Reading experimental results and analyzing the evidence.
Okay, the run is done. But you can't just glance at the final accuracy number and call it a day. Reading these loss curves is where the real detective work happens. It's the detailed story of your model's journey. You really need to run every set of results through a checklist like this. Are your best trials actually just severely overfitting? Is there some crazy step-to-step variance late in the game, meaning your final number is just a lucky bounce? Are the trials actually still improving right at the end, meaning you pulled the plug too early? Or did they saturate way before the final step? You absolutely have to examine these curves to spot those hidden optimization failures before you trust that single final metric.
And this is where isolation plots become your best friend. When you want to see if a change actually helped, you plot only the best trial across all the nuisance variables. By optimizing away all those nuisances first, you filter out the noise. Isolation plots give us a true, undeniable apples-to-apples comparison of the scientific hyperparameters we care about. To really hammer home how critical this is, the playbook drops this incredible piece of wisdom from AI godfather Geoffrey Hinton. Every time you plot something new, you learn something new. The big takeaway here is to automate your plotting infrastructure. Seriously, don't wait around to generate plots manually. Have your pipeline constantly, automatically visualizing basic hyperparameter axes and loss curves so you literally never miss an insight.
Section 6. Refining and launching, moving from exploration to exploitation.
This is the moment we transition from just exploring our model's behavior to actually exploiting that hard-earned knowledge for a production launch. But before you push that launch button, a huge warning. Do not let random noise trick you. If a new configuration barely squeaks past your old one, it might just be variance. You've got to account for trial variance, which is stuff like lucky random seeds or data shuffles. Study variance, where maybe your search procedure just got a lucky hit. And data collection variance, like random validation splits. Always ask yourself if that tiny improvement is actually worth the extra complexity you're adding to your system.
And here's the final pivot. For the exploration phase, the researchers highly recommend using a simple, uniform, quasi-random search just to get a feel for the space. But once that exploration wraps up and you know exactly what your sensible ranges are, it is finally safe to hand the keys over to the heavy hitters. You can unleash advanced black box Bayesian optimization tools, like open-source Vizier, to run that massive, automated final production search. By following this playbook, you are fundamentally replacing guesswork with hard evidence. You stop throwing spaghetti at the wall, and you start running a rigorous, predictable laboratory. So my challenge to you is to apply this exact mindset to your pipelines today. Go categorize your variables, isolate your metrics, and ask yourself, what surprising new insights will your very next isolation plot reveal? Thanks so much for hanging out with me on this explainer. And hey, happy experimenting!